Hey everyone, welcome to today's Explainer. We're going to play the role of spatial detectives today, decoding the literal building blocks of geometry. Ever look at a massive city map, a blueprint, or even the layout of your favorite video game and wonder, how is all this so perfectly structured? Well, it all boils down to some highly precise rules, and today we are diving right in to unpack them. Here is our agenda for today. First, we'll build our geometry toolkit. Second, we're mapping the coordinate plane. Third, we'll look at representations versus proofs. Fourth, we'll do some geometry knowledge checks. And finally, a recap and transfer question. Our main target today is to use precise geometric language and ordered pairs to describe points, lines, segments, rays, planes, axes, and the origin. Plus, we'll figure out exactly why a diagram is just a representation and definitely not a mathematical proof. All right, Section 1, Building the Geometry Toolkit, the essential building blocks of geometry. Okay, so just like you need an alphabet to write a sentence, you absolutely need fundamental concepts to build shapes and spaces. Let's start with the absolute basic building block, a point. Imagine a point as an exact, hyper-specific location in space. It has literally zero length, no width, and no depth. It's totally zero-dimensional. We usually just represent it with a single dot and name it with a capital letter. It's the anchor for literally everything else we're going to build. Now, what happens if you take that point and stretch it out forever? You get a line. A line is perfectly straight, one-dimensional, and has absolutely zero thickness. But the real kicker here, it extends infinitely in both directions. In geometry, we show that infinite stretch by putting small arrows on both ends. It just keeps going and going. Now, unlike a line segment has two distinct fixed endpoints. It definitively does not go on forever, and because it's bounded like that, a line segment actually has a measurable length. That's a super critical distinction when we start calculating distances later on. Next up is a ray, which is kind of a cool hybrid of our last two ideas. It starts at one fixed point, we usually call that the end point or origin, but then it shoots off infinitely in the opposite direction. Think of it like a laser pointer or a beam of sunlight. It starts at a specific source and just shines endlessly outward. Okay, let's level up from one dimension to two dimensions. When we do that, we create this flat surface known as a plane. A plane has length and width, but still no depth. And just like a line, it extends infinitely in all directions. Picture an endless, totally flat sheet of paper floating in space. So the big takeaway here is mastering the distinction and the standard notation between these core pieces. A line flies off infinitely in both directions, which is always marked with arrows. But a line segment is just a slice of that line, securely bounded by two endpoints, making it perfectly measurable. Nailing this notation is pretty much the secret to speaking the language of geometry perfectly. Moving right along to Section 2, Mapping the Coordinate Plane, overlaying a grid on our 2D plane. Now that our toolkit is packed, let's navigate these infinite spaces by laying down a mathematical grid. Let's walk through a precise practice example together to see how this works. Say we need to find the ordered pair 3, 4. Step 1, we start dead center where the perpendicular axes cross. That's the origin, or 0, 0. Step 2, we read our numbers. Step 3, we take that first coordinate, the 3. That x value controls our horizontal position, so we move exactly 3 units to the right along the horizontal x-axis. And finally, step 4, we take the second coordinate, the 4. That y value gives us vertical position, so we move 4 units straight up along the y-axis. Drop a dot right there, and boom, we've precisely pinpointed the location 3, 4. All right, Section 3, Representations versus Proofs, why we can't always trust our eyes in geometry. Okay, so we can plot points and draw lines, but now we gotta talk about the strict rule of law when making geometric claims. Here's a universally accepted rule. A diagram is a representation, not a mathematical proof. Honestly, our eyes get tricked all the time. A quick sketch is really just a blueprint or a visual aid. It absolutely does not definitively prove that a mathematical claim is true. So what actually does prove a claim? If you want to state that two lines are perpendicular or a shape is a square, you can't just say, well, it looks like it. You need hard mathematical evidence. That means relying on precise geometric definitions, utilizing accurate measurements, doing formal geometric constructions with tools, or leaning on established mathematical theorems. In geometry, logic always trumps eyesight, every single time. Let's test that out in Section 4, Geometry Knowledge Checks.
testing our spatial detective skills.
We've covered some serious ground, from zero-dimensional points to the laws of proof. Time for a quick check. Imagine you're looking at an ordered pair on a coordinate grid. Which coordinate shifts your horizontal position? Which one shifts your vertical position? And exactly how do you verify that location? Think back to our practice example a minute ago. Well, it breaks down super cleanly. The first coordinate, the x value, is entirely in charge of your horizontal movement. The second coordinate, your y value, handles the vertical movement. And to verify it, you just trace your path. Start right at the origin at 0, 0, slide left or right along the horizontal x-axis, and then travel straight up or down parallel to the vertical y-axis. Okay, check number 2, testing our rule of law. If you're looking at a diagram and it shows two lines that look perfectly parallel or two segments that look like they're the exact same length, is that sketch alone enough to mathematically prove it?
That is a resounding no. A sketch is literally just a visual representation. To definitively prove lines are parallel or segments are equal, you've got to use a specific definition, an exact measurement, a formal construction, or cite a known geometric theorem. Seeing is definitely not believing here. Proving is believing.
Which brings us to Section 5, Recap and Transfer Question, wrapping up our geometric blueprint. We've officially built our geometric foundation, mapped the grid, and laid down the law of proofs. So here's your quick 3-sentence recap. Points, lines, segments, rays, and planes form the very foundation of geometry. The coordinate plane utilizes ordered pairs to precisely pinpoint horizontal and vertical locations starting directly from the origin. And always remember, a geometric diagram is just a visual representation, while actual mathematical proof requires specific definitions, exact measurements, formal constructions, or established theorem.
To wrap things up, I want to leave you with this provocative thought. If someone handed you a map of a totally unfamiliar city, laid out completely on a coordinate grid, how would you use the origin and ordered pairs to figure out the exact spatial relationship between two specific landmarks? Take a little time to think about how you can apply these spatial detective skills to the real world. Thanks for hanging out with me on this explainer, and keep exploring the geometry all around you.